All right, so we're in section 4.4 at the end of chapter 4 now, and previously in section 4.3 we spent our time looking at the Hindu-Arabic numeration system and doing arithmetic in that system. Hindu-Arabic, as we've said a couple of times already, is a base 10 positional numeration system where the individual place values of each digit represent a power of 10. Something else we've mentioned is that the number 10 is not especially significant. The reason we ended up with a base 10 system is because we have 10 fingers. And historically, math and keeping track of numbers, counting, kind of originated with finger counting. So it's just sort of something that was carried on from those, ancient counting principles, I guess. But the number 10 doesn't have any mathematical significance beyond that. In fact, depending on what we're using numbers for, there's actually other numbers that work far better as the base of a numeral system or a numeration system. In particular, if you have any interest in computer science or have kind of heard some of these terms before, in computer science we tend to use binary, which is a base 2 system, octal, which is a base 8 system, and hexadecimal, which is a base 16 system. Notice all of these are powers of 2. The number 2 is far more useful as a number base in computer science, and we'll kind of talk about that towards the end of this section. But what I want to do is start familiarizing you with working in alternative number bases, and in particular, as the name of this section implies, we're going to work on converting between different number bases. So one thing we're going to do as sort of a convention throughout this section is if you ever see a number that's written with no subscript on it, if I just see 124 or something like that, we're going to interpret that as a number in base 10, since base 10 is sort of our default number base. But if we want a numeral or a number to represent something in a different base, we're going to use a subscript to indicate that. The subscript will spell out whatever base we're using. So for example, if this number 452 is in base 6, then I'm going to put a subscript of 6 there. One thing I want to point out also is that the way that I read that number 452, I didn't say 452. And that's because in a different number base, that's not the number 452, even though that's what it looks like. In a different number base, this is not the hundreds place. This is not the tens place. This will be the ones place. That's the only place value that's going to be the same regardless of our number base. In fact, in a base 6 system, this will be the sixes place, and this will be the 36s place. Different place values have to represent powers of whatever your choice of your base is. So to give you an idea of what I'm talking about there, let's take an example of a number that's in base 3. 1201 are the digits in this number, and it's in base 3. Just like in decimal, in our decimal system, our base 10 system, each place value, each digit occupies a place value, and each of those place values represents a different power of your base. So in this case, these are going to represent powers of 3. The digit itself has a face value which we multiply to that power of 3. So if I wanted to write out this number in expanded form, it would look like 1 times 3 to the power of 3, 2 times 3 to the power of 2, 0 times 3 to the power of 1, and then 1 times 3 to the power of 0, and then I add each of those. So if this were a base 10 number, as we saw in 4.3, writing this in expanded form would look similar, but I would be using tens as the base of these powers here as opposed to 3s. So really a different choice of number base changes the number we're using here, the number we're raising to an exponent. And again, if you go from right to left, the power on that base starts at 0 and increases as you go towards the left. Okay? So one other thing that's important to point out is that the digits that are used in a number in a particular base all have to be less than the base itself. Notice that here I use the number 3 as my base. And all of the digits, 1, 2, 0, and 1, all of those digits individually are less than 3. That's a necessary requirement of any number written in a particular base. The same is true of decimal, as you know. In a decimal system where we have a base of 10, the digits that we use are 0 through 9. Each one of them is individually less than the base itself. Up here, another example, 400, or remember, I almost said 452. It's not 452, but 452 in base 6. Each digit is less than 6. That always has to be true of a number written in a particular base. So let's do an example. I want to convert the number 412 in base 5 to decimal form. And really all this amounts to is writing this in expanded form first, and then evaluating that expanded form, doing the arithmetic that's implied there. So 412 in base 5 literally means 4 times 5 squared plus 1 times 5 to the power of 1 plus 2 times 5 to the power of 0. And I'm just going to work this out using the arithmetic I already know how to do. This is the same thing as 4 times 25, that's what 5 squared is, plus 1 times 5, that's what 5 to the power of 1 is, plus 2 times 1, that's what 5 to the power of 0 is. 4 times 25 is 100, 1 times 5 is 5, 2 times 1 is 2, and this adds up to 152. And I don't need to write 10 down here because, again, when you don't write something for the subscript, it's implied that it's a decimal number, a base 10 number. Okay? So notice again, all I did to convert into decimal from a different number base is I wrote that number in expanded form using the base that was indicated, and then I just work everything out until I have a single number. Okay? Now, that's the easiest type of conversion that we do, because really all of the arithmetic here is done in base 10. So we're familiar with base 10. There's nothing really new happening there. Going the other direction is a little trickier, and we're going to look at a couple of methods for doing this. And by the other direction, what I mean is if I give you a number that's in base 10, and I want you to convert that number into a numeral from a different number base. So there's a couple of different ways that we can go about that. And I kind of talk about that here, but it's easier to illustrate with an example. So let's take a look at an example. I would like to convert the number 924 to a base 4 numeral. Okay? And what this means, because there's no subscript here, again, that means that this is a decimal number. It's in base 10. In order to write it in a base 4 numeral, I have to start thinking in terms of powers of 4. So I'm going to start writing out. Sorry about that. I'm going to start writing out some different powers of 4. So for example, 4 to the power of 0, that's equal to 1. 4 to the power of 1 is, of course, it's 4. 4 squared is 16. 4 cubed is 64. 4 to the power of 4 is 256. 4 to the power of 5 is 1024. And I'm actually going to stop here. And the reason for that is because, again, I'm thinking in terms of how many of each of these can I fit into this number. Now, 4 to the 5th power, which is 1024, is bigger than 924. So this doesn't fit into this. I'm not going to use that. But the largest of these powers of 4 that's still not exceeding the number 924 is this guy right here, 256. So let me try seeing how many 256s there are in the number 924. That's the same thing as doing a division problem. What is 924 divided by 256? And again, I'm choosing as my divisor the largest power of my base that still doesn't exceed the number 924. That's this guy. If I do the division here, I would see that this goes into 924 3 times. 3 times 256 is 768. And then if I subtract, I should get 156, which would be my remainder. Okay? So I'm seeing here that the number 256 goes into my decimal number, 924, 3 times. That means I'm going to have a 3 in my 256's place. Remember, each place value represents one of these powers of 4 now. So there's a place value for that, and it's got a 3 in it. Next thing I want to do is take a look at my remainder. After 256 goes into this number 3 times, it leaves 156 left over. And so now I'm going to keep working my way from the bottom to the top of this list and asking how many times does the next number base, the next power of 4 down go into what's left of this number. That would be the remainder. So now I'm going to take my remainder, 156, and divide that by the next power of 4, which is 64. Okay, so now the question is, how many times does 64 go into 156? And you should see that it goes in twice. 2 times 64 is 128. If I subtract, that gets me a remainder of 28. Remainder 28. Okay, because 64 went into this number twice, then there are 2 64s, so that means I should be putting a 2 in my 64's place. Okay, then I repeat this process. I have a remainder of 28, and I want to see how many times the next power of 4 down, or up really, goes into that, 16. 16, of course, is going to go into 28 only once. 1 times 16 is 16, and when I subtract, I get a remainder of 12. So if 16 fits into what's left only once, then I only have a 1 in my 16's place. Then go to the next power down. 4 is my new divisor, and I'm dividing my previous remainder by that. 4 goes into 12 exactly 3 times. Now, in elementary school, when you learn how to do long division, if you get a remainder of 0, they usually tell you not to write the remainder of 0. But in this case, I'm going to, because I need to use that in one more step. But in my 4's place, I have a 3, because 4 fit into what was left of this number 3 times. Okay? Finally, that's my 4's place. I still need a place for my 1's. I haven't reached the top of this list yet, and so that's where this remainder ends up getting used. I'm going to divide 4 into 0. Now you can divide 0 by a non-zero number. You can't do it the other way around. So this is okay to do. 4 goes into 0 0 times and leaves me with a remainder of 0. But really at this point, the quotient is the last thing that we need. I have 0 left of this number, so I don't need anything in my 1's place. Okay? That means that this number can be written in this notation. 32130 in base 4. That's my answer. Okay? So that's one way of taking a number that's given to you in decimal and converting it into another number base. And if I wanted to check to make sure I did this right, what I could do is use basically work through this in reverse like we did in the first example, write this in expanded form. Remember, this would represent 3 times 4 to the power of 4, or 3 times 256, because this is the 256's place. This is the 64's place, so I could think of this as 2 times 64. 1 times 16, 3 times 4, 0 times 1. Multiply the face value of each digit by its place value, which I can see in this list. And then if I added all of that up, I should end up with 924. I'm going to leave that to you to check, and it's a good exercise because it's always good to know how to check if you got something right or wrong. Okay, now this process, even though it works and it's a very logical approach, it can be kind of difficult. Especially if you're doing everything by hand. And the reason for that is because you start with the largest power of the base that you're working with that doesn't exceed this number. And what that means is that you're dividing by potentially large numbers. If you're doing everything by hand without the aid of a calculator, that might take a little bit of time to work through. It wasn't the worst thing in this example, but if for a larger number base, that can actually end up being fairly difficult. Fortunately, there's an alternative approach that allows us to only ever have to divide by what the base is and not divide by powers of that base. I just realized I made a mistake here. I wanted to not divide by 4. I wanted to divide by 1. That was the next place value. I get the same result, though, so it doesn't change anything. So what I would like to do is go back to the previous example that we did and rework it. So I should be getting the same answer, but using a different approach. I want to see what happens if I just take my number 924 in decimal and divide by 4 repeatedly. The number 4 being the base that we're converting to. So if I take 924 and I divide that by 4, okay? 4 is a smaller divisor. The division takes a little bit longer, but the steps are easier in general, so there's kind of a trade-off. 4 goes into 9 twice. That gives me an 8. I subtract, giving me a 1. Bring down my digit of 2. That gives me a 12. 4 goes into 12 3 times. And then I do 3 times 4, which is 12. Subtract to get a 0. Bring down my digit of 4. 4 goes into 4 once, and then I do 1 times 4 to get 4. That gives me a 0, so I end up with a remainder of 0. Now what we're going to do next is take the quotient, which was 231, and turn that into my dividend, meaning the thing I'm dividing by 4 in this case. So I'm going to keep taking the quotient and using it in a second step where I go here and I divide by the same number again, the same thing that my base is, 4. Because, just for the sake of time, this is long division, and I just realized I was writing all of that off the screen. Sorry about that. Long division is it's arithmetic, and some of you might need a little bit of a refreshing on it, but this is not an arithmetic course, so I'm not going to work through all of those steps. I'm hoping you can fill in some of the blanks here. I'm going to give you just some answers. This is going to amount to 57 with a remainder of 3. If I were to work those steps, then I take that 57 and do a division problem with that, still dividing by 4. I would get 14 in this case with a remainder of 1. And then if I do that 14, divide that by 4, I should get 3 with a remainder of 2. And then finally take that quotient 3, divide that by 4 again. 4 goes into 3 0 times, and I'm going to get a remainder of 3. And at this point, we are done. Once we get a quotient, or once we've gotten this dividend down to where it's less than 4, I'm going to be getting a 0 for my quotient here, and that's what's telling me to stop, basically. Now, look at the remainders. 3, 2, 1, 3, 0. Compare that to our answer. 3, 2, 1, 3, 0. If I read these from right to left and then write them in reverse order, 3, 2, 1, 3, 0, I got the correct base 4 numeral for that 924 that was originally in decimal. I got the same answer as we were expecting. This approach will always work. I'm not really going to dig into the reason why. It's not too hard to explain, but what I wanted to do here is just give you a sense of how the method works. If you're interested in why, I would encourage you to ask in the discussion forum, and I can give you a more in-depth explanation there. But this is the approach that I'm going to be using for further examples. Okay? Now, so far, the number bases that we've looked at, in examples at least, have been base 5. We did an example where we were in base 5, and then we just did a couple of examples where we were in base 4. What we have not done is looked at what happens when you have a number base that's larger than 10. Those were all smaller than 10. And if you notice, I was using the same digits that I'm used to, 0, 1, 2, and 3. I'm allowed to use those digits in base 4, for example. But what do we do if a number has a base that's larger than 10? Because the number base determines how many digits you need to have available to you. Again, in base 10, we have a total of 10 digits that are available to us, 0 through 9. That's 10 digits cumulatively because we're counting 0 there. So the base of a number tells me how many digits I need. What if I'm working in hexadecimal, for example? That's a base 16 system. That means I need to have 16 digits available to use in my in those different place values. I can use 0 through 9. That gives me 10 digits to use, but that means I have to find 6 more symbols to use as digits. And what we do is once we get past 9, we start using capital letters to represent digits. So A is going to have a face value of 10. B is going to have a face value of 11. C is going to represent 12, and so on. Okay? So with that in mind, let's think about how we would work in such a system. Let's suppose I'm given this number, 5A1E in base 16. I want to convert that to decimal form. Now, when you look at that, it doesn't look like a number at all, right? You see letters in there. It feels like it feels like a code or something, or I don't know. But in base 16, this is as valid of a number as 5 is in decimal, So we just need to know how to interpret those letters. So 5A1E in base 16 is equal to, now let's think about what these number bases are. So we're in base 16, so these place values represent powers of 16. This is 16 to the power of 0, 16 to the power of 1, 16 to the power of 2, 16 to the power of 3. So that first digit, 5, represents 5 times 16 to the third power. Plus, now I'm not going to multiply by A because, again, A is just a symbol that represents a specific value. Up here we said A represents 10. So when I see an A here, what I'm really multiplying by is 10 times the next place value, which is 16 squared. Okay? Then I'm going to add to that my next place value, which is 1, or my next digit, which is 1, times the place value it occupies. Oop, not 12. 16 to the power of 1, plus E. What does E represent? Well, if A is 10, B would be 11, C is 12, D is 13, E is 14. So this is going to be 14 times 16 to the power of 0. I'm going to skip doing several steps like we did in our first example. This can either go into a calculator or you can do a lot of work by hand, but what you should end up with is 23,070 as a result. Okay, you can check that in a calculator if you want. We should also be able to go the other direction. So convert, say, for example, the number 709. This is in decimal because there's no subscript given. We want to convert that into hexadecimal, base 16. And again, we use repeated division in order to do that. 709 divided by my number base, which in this case is 16. 16 goes into 709 44 times and is going to leave me with a remainder of 5. And again, just want to emphasize, there is work that I'm leaving off here. And that's just because it's time consuming and I know you should be able to fill in the gaps here, even if you need to practice long division a little bit. Then remember, I take my quotient, 44, divide that by 16 again, which gives me 2 with a remainder of 12. Then I take that 2. Now that my quotient is smaller than the thing I'm dividing by, I am expecting a quotient of 0 up here. The remainder would be 2. That tells me to stop when I get that quotient of 0 right there. Then remember, the way that we write our number in hexadecimal is we read the remainders off, but in reverse order. So 2 is going to be my 256th place. That's 16 to the second power. In my 16th place, I have a 12, but you don't want to write a 12, right? That's 2 digits, and we want to represent that by a single symbol. Well, remember, in hexadecimal, we let C represent the number 12. So where I'm getting a 12 here, I want to call that C. And then finally, in my ones place, I should have 5. And this is in base 16 now. Okay? I'm going to stop this video here, and we'll probably finish things up in the next one.